Hello everyone and welcome to the 43rd lecture of the course Advanced Structural Analysis. This is the 9th week. We have covered the basic method of the stiffness analysis. We looked into the analysis from the standard regular stiffness method, which is the part of the standard displacement method, and eventually we looked into the method which can be implemented in the computing environment, and there we were able to identify the methods for the general plane structures as well as the space structures. So, we plan to take the given content on the matrix based analysis or the stiffness method up to the week 8. We had extended lectures on the 3D space frame related problems, and with that now we would like to start with a new topic, which is the geometrical nonlinearities in the given system. So, the given content which we will try to cover primarily will introduce the basic idea of the nonlinearity, the various types of the nonlinearity which can exist in the given problem, and particularly we want to concentrate upon the geometrical nonlinearity through these set of lectures. Eventually we will also move to the material nonlinearity in the successive lectures, and then we would like to continue with the similar relations for the kinematic relations of the truss members. So, as we understand that up to now whatever we have been doing is valid within the linear framework of the structural analysis, and there is a very standard concept of the material nonlinearity or the geometrical nonlinearity which many of the times we regularly hear. So, now we want to introduce these particular concepts in the context of the structural mechanics problems. Before going into it, what we can realize that in a regular problems of the structural analysis which we have followed till now, we followed a standard order that the equation at the end of the formulation were written in the form of A, which is the action field of the given structural component, equal to the structural stiffness of the given system into the delta, which is the deformations of the given system. So, we find multiple ways in which the similar equation is written. Many people write it as P equal to K delta format also, where P happens to the force, K equal to the stiffness of the given system, and delta is the unknown displacement parameters of the given problem. Now, in most of the problems which we tackle in our general engineering applications, we consider that the stiffness of the given system is constant, which means that if I come up with the given system of the load versus displacement curve, and considering that the stiffness value of the given system is a constant value, and I am trying to do, of course, there is a load vector which we typically assign, which has a multiple values, multiple components of the given system. Similarly, delta also is a vector which contains multiple values in it, but if I just look at one compatible set of load and the displacement correspondence, I realize that the relationship will come out in a manner because the stiffness parameter or the K value of the given system is constant. So, it will just be going with a constant slope through the given section, which means that if someone comes up with the load of say a magnitude P1, I can get the value of the deformation corresponding to it, say delta 1. Subsequently, if I further apply another load on the given system, say with the increased value, and the load reaches to a magnitude of P2, I can still follow the same equation because the stiffness value has not modified, and I can just evaluate the new deformations of the given system, say which is delta 2. So, now as a general idea, one can always talk about that if you apply the load on a given system where initially some value of the load of P1 is applied, and there was a deflection which was provided to the given problem, say of the magnitude delta 1, I further provide the another load of say the delta P value on a similar system, but in a different situation, and I get some value of the displacement for this case as well, say delta which is del W of the given system, say a small variation in the displacement of the given problem. Now, if I want to say that what will be the displacement with respect to the total load of P1 plus delta P in the given problem, so one can easily deduce it that as the linearity of the stiffness matrix is maintained, one will be getting the total displacement of delta 1 plus delta of del delta in the given problem. So, this idea of understanding the overall deformations of the system with respect to a linear stiffness relationship is much more easier for the regular problems. But now the problem can become much more complicated if we come up with a stiffness matrix which itself is a function of the unknown deformations or the delta of the given system. It could also be the function of the respective forces which are active on the given system. And in this manner, if we say that the amount of the stiffness which is identified for a given problem is not a constant value, but it keeps on modifying itself as the value of the deformation or the active load on the given system changes, the system can now no longer be identified with the same linear relationship. So, what we are typically talking about is now a system in which as the delta or the load value increases respectively, any one of the parameter we can consider that we are increasing the given value, and corresponding to that we will try to look at the changes which are taking place in the subsequent value. So, these relationship will no longer be defined by the linear relation, but rather now the stiffness value will keep on changing itself, and what we mean by keep on changing is that the tangent on the curve at different positions is going to take the different values of the given system, and this makes the problem nonlinear. So, in a typical structural framework which we adopted till now, we considered that the general material properties or the deformations which the system is going to take place, those are also small, or the elastic properties of the given system, they were such that the stiffness properties were constant. They were considered as a constant value throughout the application of the load on the given system. What it means as when we evaluated the stiffness parameters, if you can recall, we had got some coefficients like E upon L, we have got the coefficients like EI upon L cube related parameters in the given system. So, these are the parameters which are dependent not only on the properties of the material, but also on the geometrical parameters of the given system. But if the geometrical parameters as well as the material parameters are kept such that the stiffness values remain constant, they do not change with the increased values of the displacements, we understand that the problem is more or less linear, and we can easily do these kind of simplified analysis in the given problem. But the moment the material coefficients, say the elastic property of the given system, or say the deformations in the system are successively large, which makes the system stiffness as a function of the displacement itself, then the condition of the nonlinearity will be introduced in the given problem, and this is the state of the condition where the stiffness changes with the changing displacements or the load parameters on the system, and this is typically known as the general nonlinearity in the given problem. Now, what changes with the overall structural analysis, as now we can anticipate that in a regular problem, if you have a stiffness value which is constant, one can easily evaluate the response of the given system. So, if I am looking for the solution of this equation, delta is the unknown parameter for me, I can easily inverse the k value and get the value of the delta unknown displacements for the given value of the load. Now, this inverse is possible because it is having a constant value, and the user can come up with some standard numerical approaches to inverse the given matrix and generate the unknown parameters of the displacements in the given system. But now, in a situations where the stiffness of the system also becomes, say, a function of delta or say the load of the given system, now taking the inverse for a given stiffness matrix will not be possible, because now it is itself an unknown parameter of the delta functions which are themselves are not known to the user at the beginning. So, now instead of doing an analysis which can be directly evaluated by inversing the given system or by solving this given linear system of equation, the user has to rely upon some nonlinear equation solution tools to evaluate the response of these given equations in the given problem. And this typically brings the approaches which we typically call as the iterative as well as the incremental analysis approaches. So, what one can easily realize that now in order to get the response of this given system, I cannot solve it as a general system. Like if we look at this problem, there is a very fixed value of the load, and for that given value there is a fixed value of the displacement in the given system, and that is what we typically evaluate based upon the constant values of the stiffness of the given problem. But now in a nonlinear problem, as the value of the displacement in the given system is identified at a point and the corresponding value of the load is located, the stiffness relationship between these two values will not remain same as we move to a different displacement of the given system. So, in order to know the response of the given system, the general analysis approaches typically rely upon tracking the given curve. We keep on moving to the different neighborhood points of the given system, keep on evaluating the new values of the stiffness coefficients at that particular point, and try to evaluate the response of the system at these successive points of the given system. So, there are standard incremental approaches which keep on incrementing, say, on the load value. With the increase in the load value, we obtain that what is the particular point at which we are trying to evaluate the displacement, and for that particular point we also cross check whether the stiffness parameter, which is continuously being modified, is giving us the correct response. In cases there are some errors, we come up with some methods in which we iterate the given solution to generate the correct answers of the given system. So, generally we understand now there are numerical approaches which typically rely upon increments as well as iterations in the given systems, and this typically identifies the solutions of the general problem. So, we will briefly look at the Newton-Raphson method in the subsequent lectures, where we will try to see that how we identify the step sizes of the increments and how do we understand the philosophy of the doing the number of iterations in the given problem to get the actual response of the given system. But the standard idea is, as a regular linear problem, we were able to inverse the given stiffness matrix, which was a constant value, which will no longer be possible in a nonlinear problem, and the solution has to be obtained using some kind of incremental approaches in which we keep on tracking the stiffness values at the subsequent points of the given system, and we keep on correcting the response of the system based upon some correction approaches in the given problem. With this idea in mind, we understand now that there are different kind of possibilities which can introduce the nonlinearity in the given system. Now, through the subsequent few slides, we will try to look at these nonlinearities. As we understand the very simplistic one, the first one is the material nonlinearity in the given system. Most of the time we have seen our stiffness relationships, those are the function of the elastic properties of the given system or the shear modulus of the given problem. And now, if we understand that the elastic properties of the given system are no longer linear, they are also changing non-linearly with the increased value of the stress and the strain level in the given system. The user has to adopt the same non-linearity in the structural analysis framework as well. So, as a simple material response which we have shown over here, the material remains or follows a simple proportionality limit up to a certain point, beyond which the system moves into a range where it is non-linearly, or it is not no longer following the proportionality limit of the given system, which means that the linear relationship holds true up to a certain point, beyond which the material goes into the non-linearity, and at certain point the system yields and moves into the continuous deformation, which is the state where the system has undergone into a plastic response, and the system will be now having a material response which will no longer be defined by the constant value of the elastic modulus of the given system. So, as we understand that moving beyond these points will lead us to a particular territory where the elastic properties of the given system are not constant values. And now, if you require a material to be used within these limits, because of course now we understand that, as a very simple example of the steel structures which is shown over here, we typically do not rely that the steel should only be used up to the linear proportionality limit. The material can also take load, a very good amount of load beyond the standard proportionality limit. So, if we want to utilize the material beyond this part, which is significantly more, then we have to adopt the nonlinear material response also in the given system. And as we consider the material response to be nonlinear, the structural analysis for the system should also incorporate that in the regular stiffness evaluation of the given system. The second one is the geometrical nonlinearity in the given system. So, typically when the systems they undergo large displacements, which could be both the translations as well as the rotations. So, this large deformation also modifies the stiffness of the given system. We will see some examples in the given problem, and the subsequent few lectures will try to look at the individual examples which will be coming across the geometrical nonlinearity. But the understanding is that as the stiffness value gets modified due to the large deformations on the given problem, so this also introduces a nonlinearity in the given problem, which means that now as the deformations are increasing in the given problem, the system will also be experiencing a change in the stiffness. This could be an increase or decrease in the stiffness, typically known as the stiffening or the softening of the given system. But the understanding is that as with the changing or the increased level of the displacements, system starts to have a modified stiffness values, we consider that this particular aspect is the geometrical nonlinearity of the given system. As a third part, also we can just note that in multiple situations where the large deformations are possible in the system, those are the flexible structures like the regular cable based members, the members which are very thin or slender, the members which are subjected to the loads which are compressive in nature, and typically those members have the standard behavior where the deformations can exceed the standard small deformation levels, and in those situations the user has to consider the change in the stiffness due to these increased level of the displacements of the given system. As a third part of the nonlinearity which can exist in the system is the contact nonlinearity or the nonlinearity due to the support conditions of the given system. So, whenever two objects they interact with each other, they have a contact with each other. So, at the contacting boundaries the system has a change of the stiffness, and this typical change of the stiffness is considered as a contact based nonlinearity in the given problem. So, if we consider that there is a sphere which is subjected to some kind of a external load or a pressure conditions on the given system. Now, at the same time the sphere makes a contact with another sphere in the neighborhood. So, up to the point the sphere is not in contact with the given geometry, the sphere response will be more or less uniformly distributed throughout the given system based upon the active load which is applied on the given problem. But the moment system makes a contact with the neighboring sphere or any other geometry, the region which is nearby to the given contact region will have a change of the stiffness that will typically be introduced due to the contact between these two surfaces, and this is also one possible way of nonlinearity which typically exists in the given system. So, at many of the situations, an example like this, that the system is undergoing some kind of a displacement, and as the system undergoes displacement at a certain state, the system will interact with the nearby object or a surface which will make the contact with the geometry, and now due to this contact at the localized locations the system stiffness will have a changes, and these local changes are typically again nonlinear, which are not following the standard linear relationship of the stiffness of the given system, and that is also becomes one possible way of nonlinearity in the given problem. So, in our present context of the discussion, we are primarily concerned about the geometrical nonlinearity of the given system. As we will move forward, we will also look at the material nonlinearity in the given system. Contact nonlinearity in general we will not be considering in this course, but those of you who are interested, those of you who are interested to do the finite element simulations of these kind of problems, they may look into the standard computational tools, and they very well define the contact nonlinearity in their standard algorithms. Now, before going into the geometrical nonlinearity, we must now understand that why it is necessary to consider the nonlinearity. The linear analysis which we were adopting till now is much more simple and easy to implement in the given system, and in fact many practical problems can be easily solved using the solutions which are much more reliable as well as safe. But at the same time there are certain aspects of the analysis which need to be considered while we are thinking about whether to switch to the nonlinear analysis or not. Now, what could be these possible reasons? The one is the functional design space may sometimes require us to have the inclusion of the nonlinearity in the system. So, as we asked in a very basic point in the last slide itself, that a cable based structure is supposed to have displacements which will be significantly large. Any slender structure will be subjected to the displacements which will be significant with respect to the overall dimension of the given system. So, in these situations the design itself is done with the idea that the structure will not be fully rigid or will not be maintaining the small deformation in the given system, but may also undergo some large displacements, and then these functional requirements cannot be fulfilled if we do not include the nonlinearity in the analysis and the design of the given system. Now, secondly, there may be some of the material requirements which may also require us to keep the inclusion of the nonlinearity in the given problem. Say for example, we are going with the soft materials, say rubber based materials of the system. Many of the computational models of the tire materials are typically done. So, if someone is trying to model the material like tire or the rubber materials, then one has to consider the non-linearity, because the material response will no longer remain linear. In fact, the material response can be very different with respect to different viscoelastic or other kind of material models as well. And in those scenarios, the inclusion of the non-linearity in the problem becomes much more important. Same is also true for the biological systems. People model the much of the biological parameters using the standard mechanical models, and in those situations, if you are trying to model, say, the basic behavior of the cell geometry, the behavior of any kind of fluidic movement in the given body system, then the understanding of the large material response as well as the large deformation cannot be neglected. So, these are some of the cases where the understanding of the non-linearity has to be introduced. Then the structural response under the extreme loading, which cannot be prevented. If we want to design our structures for the extreme wind effects or the earthquake, very here in the Bhubaneswar we get the regular cyclones. So, designing the structures in these situations may not be very much possible if we do not include the non-linearity in the given system. If we want our structure to remain only linear under the application of these catastrophic effects, probably the design will become so much uneconomical, it will become such a large section of the designs which will not be feasible. So, to make the system responsive as well as flexible enough to undertake these load scenarios, we have to adopt the nonlinear analysis in the given system. And as we already discussed, that there may be the change in the philosophy of the design itself. If you want to use the material strength beyond the regular proportionality limit, beyond the linear elasticity limit, then we have to adopt the nonlinearity in the given system. So, with these basic and also the contact of the boundaries as we just discussed. So, these are the regular problems which we typically introduce. In fact, in the real life scenarios, the most of the structural components which are typically designed, which exceed a certain size, they have to be modeled with respect to the nonlinear analysis as well. And this becomes much more important because the overall design, which is safe and at the same time which is economical, cannot be fulfilled without the inclusion of the nonlinear effects of the given system. Now, with this idea in mind, we start with the first discussion, which is the geometrical nonlinearity in the system. So, as we said that the geometrical nonlinearity is typically a way in which the system changes its stiffness as the amount of the displacement changes in the given system. So, the systems which are subjected to the large displacements, typically they show the change in the stiffness values with respect to the large displacements of the given problem, as the stiffness value can increase or decrease both the ways. So, we typically consider that if the stiffness increases, it is typically the stiffening of the given system. If the stiffness decreases, it is typically the softening of the given system. So, now what we understand that, as a very simple example, I have considered a simple pulley which is hinged to two of the points somewhere on a roof. You can simply consider that we mostly put the clothes outside on some hangers, and these are, say, those rope wires. If I just want to put a small weight at the center of this given system, and I want to put a weight such that I will get a deflection on this system, say, of a value of 1 unit. I want to get this 1 unit of the displacement in the given system. So, I need to pull it, downward. As I will pull it, so probably I am just giving some numerical value so that the things make some sense. So, if I initially pull the given system, I will probably require a load of, say, 10 Newton in the given problem. And as you pull it by the 10 Newton of the load, the system will very easily come down by the unit displacement which you wanted to provide. So, this is the new shape the catenary will take. Of course, it will not be this much bent, but you can understand that the system will come down. As I want to further subsequently increase the same amount of displacement in the given system, so I further want to go with the delta 2 with again a new increment in the system which is of the same magnitude, 1 unit. So, what do we expect? Do we require the similar amount of force? Probably no. I need a little larger amount of force in the given system. So, as I start with the same amount of displacement from this position where the system has already been displaced, and I further want to pull it down, I will now require a larger amount of force, say a 50 Newton of the force, and that will probably bring down the system from this position to the new position. So, let me say that this is the 50 Newton of the force. Now, subsequently someone still wants to pull this down with another increment of 1 unit in the given system. So, as I want to pull it further down, I understand that the amount of the force which I need to require to pull the system will be significantly large. It could go as high as, say, say 200 or 250 newtons. So, what typically is happening in a given system, as I am increasing the amount of displacement with the same magnitude, with the subsequent iterations or with the subsequent increments in the given displacement, I require a larger amount of force in the given system. That means there is some stiffening which is taking place in the given system, or ideally I can say that the stiffness of the given system is increasing as I am trying to pull the system more downward, and this is offering more resistance to give a same amount of displacement in the given problem. So, this is a typical simple example by which we can understand that the stiffness of the given system does not remain constant, but as the displacements are changing with the given problem, the amount of the stiffness which the system is offering is also getting modified. Now, one must be very careful while we are doing this whole experiment, say virtual experiment. We considered that this whole process is carried out with the material being within the linear limit. So, it is not that the material is moving in the non-linearity ranges, and that is where the changes are occurring. The material is very well within the linear elasticity, but what is happening to the system is all due to the large deformations in the given problem. So, now one can easily understand it in a simplistic sense as well, that as the system is getting pulled downward, somewhere the angle at which the member is inclined with respect to the downward load is also increasing. So, as the angle is increasing, so the amount of the resistance which these forces are now going to offer is also significantly increasing for the given problem. So, there is a kind of stiffening which the members are experiencing as you are trying to pull the system downward, and as the angle has increased, so the user has to subsequently pull it with the larger amount of force to make the same amount of displacement in the given problem. As a second case, I can go with a simple example like a beam column system in the given problem. What typically happens that if we have a lateral load which is also active along with the longitudinal or a compressive load on the given system, typically the system will undergo some amount of deflection, and some amount of lateral deflection on the system will appear like this. So, if I say that the system has moved by some amount of displacement in the lateral direction, say the delta value, now the load which was active on top of the given system will also be applied over here. So, at any given point, if I evaluate that what is the amount of moment which is active at the bottom of the given system, so this amount of moment m can be written as h into the given height of the system, say L, and at the same time there is an extra moment which is appearing on the given system, which is due to the vertical load which was active on the given system. So, the vertical load which was initially aligned along the length of the given member and which was generating 0 moment has now shifted away by some distance, and due to this amount of the lateral displacement delta, the system is now able to experience an extra amount of moment, and if I introduce it, it typically gets the value of P into delta in the given problem, and that typically makes it possible for the given system that a system will now be subjected to a possible load which is not only generating the simple moment due to the lateral load, but is also experiencing amount of moment which is due to the compressive load which was active on the given member. So, as the system undergoes with the lateral deformations more and more, this amount of delta on the given system will also keep on increasing, and subsequently the amount of this moment, the secondary moment on the given problem, will also keep on increasing on the given system. So, as we understand that the moment on the given system with respect to the lateral deformations is increasing, and these are only possible if the system is having a significant amount of or the large displacement in the given problem. If we expect that the system has a very small amount of lateral displacement which is nearly negligible, then we can consider that the P into delta will not have a significant effect. But in cases where the value of the displacement, the lateral displacement is significant, the user also need to define or user also need to consider this effect effectively in the given problem. Now, one can also consider that the behavior of this moment can also be different. If I, instead of considering the compressive load, I come up with a tensile load on the given problem. So, as I provide a tensile load on the problem, so this load will be now active on the given system like this. So, if I just consider the member like this, and somewhere I provide that this is now the tension load which is active on the given system, with the same magnitude. So, what I now realize that due to this lateral displacement of the given system, the amount of the beyond the regular value of the moment h into L, or it can decrease beyond that value based upon the load is either compressive or tensile in the given system. Now, moving forward, we have the next case which we consider that why we require some of these structures to be considered critically for the large deformations. So, as we understand that large deformations is required for the design as well as the analysis of certain problems, but at the same time it may become much more critical for some of the members, because these members, as they modify their stiffness with the increased value of the deformation, can also go into such a range where the stiffness drop may become significantly critical for the given system. It especially occurs in the problems where the membrane loadings are active on the system, like the shell structures or the arches in the given problem, or it also happens with the columns under compression, as we just saw. So, in these kind of problems where such loads are active, which are going to decrease the value of the stiffness of the given system, as the stiffness value reduces to a significant value, the stiffness can become critical for the given system, and such cases are typically considered as the instability in the given problem. So, what we understand now, as the structure which undergoes large displacement or rotations, the stiffness modifies, and now there is a possibility that this stiffness value which has been decreased on the system becomes significantly low, such that the material is no longer able to resist the external loads active on the given system and undergoes large amount of displacements like a free fall or a free translations or the displacements of the given system. If the such cases occur where the system is subjected to a sudden instability with the increased amount of load, the typical system is considered to be unstable, the system which has gone in the instability, or we consider that these systems have buckled under the given load. So, this is also one of the aspect of the problem which we will subsequently discuss in the next few lectures. As a very simple case of the analysis, we have already highlighted that we typically consider that the stiffness of the given system as reduces significantly, the system may have a possibility that it will undergo large deformations, and those deformations, if they become significantly large where there is no control on the possible displacements being taken place by the given object, we typically identify that the system has reached into a failure mode or a buckling mode of the given system. But in some of the cases, the system may have a small possibility of a large deformation, but immediately it just modifies from its one particular shape and moves into a second stable shape of the given system. What we typically mean by that, as we are considering the given problem, we understand that the system should have a large deformation as it is undergoing the possibility of the buckling. So, with the increase in the load, the system will try to show that the displacement is significantly increasing, but then all of a sudden the system will have a switch in the configuration of the system. So, if you just see this example, someone is just trying to pull the given system inward, and as we are trying to pull it, initially the system is moving significantly such that it is bending too high, but all of a sudden the system modifies its shape, it modifies to the different profile, and now the system has again gained some level of stability in the given system. So, this could be defined by some kind of a profile like this, where the system goes under a displacement significantly large, then all of a sudden it reduces the load level such that it appears that the system is moving with the instability or the buckling failure, but all of a sudden system snaps and moves to a new position, which is the another equilibrium position of the given system, and then system may continue for a subsequent condition or the duration to further take up the load in this new configuration which the system has adopted. So, this typical process is called as the snap through in the given system, in which system moves from one stable configuration to another stable configuration, and we typically model these systems also using the standard buckling problems. We will later see that the analysis of the buckling problems can be done using the standard eigenvalue problems. We identify that the overall stiffness of the given system which we identify is made up of the stiffness of the linear system and the stiffness due to the geometrical nonlinearity in the given problem, and this geometrical nonlinearity of the given system, which is typically identified, will be giving us some possibility to convert the system. I am just writing at this moment in a simplified manner, but if I write the equation in this manner, that any increment in the load is identified by this stiffness into the change in the displacement of the given system. So, in a situations of the buckling, one can easily come up with the condition that the system is no longer able to take the extra load in the given problem, which means that I can identify that the k of L plus k geometrical into du is nearly equal to 0. This eventually means that the displacement parameter of the given system, it cannot be 0 all the time, because that is a trivial solution for the given problem. So, the only possibility is that I should put the determinant of this given system equal to 0, and that gives us one possibility to define the standard eigenvalue problem in the given system. So, with this part we will try to move ahead, and we will try to see the various cases of the geometrical nonlinearity as well as the buckling analysis of the given system. With this we stop over here. Thank you everyone.